evaluation can look like. And in all of those direct evaluations yesterday, they were all functions, continuous functions, parabola, line, line, line. There were no real glitches. This has a glitch in the form of a hole at 2, right? But limits still exist at holes. And was this a hole also? I can't remember. Did that have a numerical answer? Or was it does not exist? No, none of them were does not exist. So they all had numerical answers. So that must have been in the form of a hole. I don't know. We have no idea what this graph looks like, correct? Right? When you initially look at it, you may think it has a vertical asymptote at 0, right? But I think they all had numerical answers, so it must not be an asymptote. So this is a graph that you're never going to know what it looks like, by hand, I should say. But just to kind of bring some more meaning behind it, 16 plus x minus 4. Uh-oh, that should have been in parentheses. And then divided by x. Why don't I see anything? Probably. Well, let me look at, no, my window should be fine. Negative 10 to 10, negative 10 to 10. Look at my table values. Okay, because they're teeny, teeny, tiny. First of all, my table is changing by 1/1000, so I'm going to make it change by just 1. And, oh, now it's starting at 0.001, so I'm going to have it start at 0. Okay, so the reason I'm not seeing anything is because it's so teeny, teeny, tiny. So my y values, I'm going to make my y window go between negative 1 and 1 and hope that that makes me see more. Good. So, like I said, it initially seems like we would have an asymptote there, but just by the nature of the fact that there's a radical in the numerator, this is kind of not, it's not a traditional rational function. So you see here now that there is a limit as you approach 0 from the left, and as you approach 0 from the right, those two arrows would be pointing at each other. There's a hole there, obviously, that we're not seeing because we do know it's undefined at 0. But the calculator, you can do like second trace, and you can look for a value not at 0, but you could do like 0.000001, kind of tell your calculator to get infinitely close to 0, and that will give you 0.12, which, does anyone have these notes handy, what the answer was? Does 0.12 sound familiar? 12 100ths would be 6 50ths, would be 3 25ths. What was it? 1/8, which is 0.125, right? Okay, so it's, I'm actually surprised that doesn't give you exactly 125, but the fact of the matter is that's kind of how you could use your calculator if you had it to just verify. And on this last one, this is, again, clearly not an asymptote at 3. It's obviously a hole of some sort. So if I type this in, 1 over x minus 1 over 3, close my numerator, and then divide it by x minus 3 is the denominator, zoom 6. Okay, the asymptote actually looks like it's at 0. I'm going to change my window and go negative 5 to 5. Zoom in just a bit. So it actually looks like I have a 0 asymptote. And that's probably because when I got rid of my complex fraction, I had a denominator of x. And then I could plug in 3s. But I do have a hole at 3 something. You don't see the hole again on here. But if I wanted to see what that limit was going to be, I could do a value at 2.999999. And what was that, negative 1/9? Winter's going to be my guy. Yeah, negative 1/9. So just a little, shed some light on that from a visual perspective. Those were all typical regular functions. Piecewise functions, and the first thing I wrote at the top, and this was more to remind myself to discuss this with you, the answer is no. Direct evaluation is not a good idea with piecewise functions, okay? Because direct evaluation is going to give you, like let's take this one for example. Direct evaluation at 2 is going to give you an answer. But that's not the right answer. Because if it's a point of transition, which obviously if you look at your 3 equations, the function rule changes. Before 2 it's this, after 2 it's that. If those two don't come together, then the limit does not exist. But if you just are looking at the function value and you plug 2 into this one, you're going to get 4. But that's not the right answer. So because of the danger of the transitioning between pieces in piecewise functions, direct evaluation is not a good idea. You want to specifically look at the limit coming from the left, which you can use direct evaluation for one-sided limits, and direct evaluation coming from the right, but see if they match. So obviously we have the picture in front of us, so we should see that the limit as we approach -1 does exist, versus at 2 it does not. Now why does it exist at -1? Obviously visually we see, but from a function equation standpoint, because when you approach -1 from the left, those are from numbers smaller than -1, so that fits into this category. You can plug -1 into here. -1 plus 2 is 1. It would be an open circle, though, if you were plotting that point, because x is not less than or equal to in this case. It's strictly less than. So this function stops with an open circle at -1, 3. The next function picks up at -1 and includes -1. We have the or equal to. So if we're coming from the right, we would plug into this equation, and -1 squared is also 1. So even though on this function the endpoint is open, on this function this initial endpoint is closed, and it coincidentally happens to be at the same spot, which really just plugs it up and makes the limit exist. It also makes it continuous, as a matter of fact, right? Okay? And then your overall limit does exist. So on that one, if you directly evaluated just by plugging in -1, you would have gotten lucky, essentially. And you can get lucky when it does exist. But on this one, if we're approaching 2, from the left-hand side, that would be this interval. So you plug 2 into there, and you would have a closed circle at 2, 4 coming from the left. Coming from the right, you plug into this equation, and you get 3. So coming from the right is different than when it comes from the left, and so the answer does not exist. Do we follow? Okay? Can you get lucky by doing direct evaluation? Obviously you can, but you should not do that for piecewise functions. Okay? When you're dealing with the limit as we approach a point of transition, where you're transitioning from one piece to the next piece to the next piece, these points of transition you should look at as one-sided functions, limits, and see if they match. Just really quickly talking about function value, f of -1 is 1, f of 2 is 4. So because this function value matches that limit, we have continuity at -1. Because, first of all, the limit doesn't even exist at 2, there's no way we could be continuous, and they obviously don't match either, so that's furthering the fact that we're discontinuous at 2. Okay, any questions? So without having a picture in front of us, the limit as we approach 1 from the left. Connor, which equation are we going to use if we're approaching 1 from the left? What? Say it again?
1 minus x.
Correct. 1 from the left is like 0, negative numbers, and so on. So we would just plug 1 into this. 4 minus 1 is 3. What if we're approaching 1 from the right? Haley, what do you think? Which equation do we plug into? The bottom one, so what would we get? 3, correct. 1 squared plus 2 is 3. And then does the overall limit as we approach 1 exist, Adam? Why not? So because f of 1 is 2 and they don't match, you're saying no. So you're getting continuity confused. So the limit does exist. The limit only requires that these two match from the left and from the right. So that does exist. The fact that these two now don't match, that means it's discontinuous. Okay? So I don't want you to have to sketch these every time, but I am going to sketch this one now that we've done it so we can sort of bring meaning to this. So when x is less than 1, so that would be the point, 4 minus 1 would be 3, so 1, 3. We have an open circle, and that would be the line. Then when x is greater than 1, it's x squared plus 2, which is a parabola, right? That's been shifted up 2 units. Do you follow? But we only want that where x is greater than 1. So another open circle at 1, 3, which is here. And then it's going to be a parabola moving forward. And then right at 1, we just have the point 2. So that's what that would have looked like. A linear coming in from the left, a quadratic going out to the right, and then this kind of isolated point. Once you're looking at it, can you see why the limit exists and why the discontinuity happens? Yes? The only way we could have kept this continuous would be to say if x equals 1, this would have had to have been 3 to plug up that hole, 1, 3. Or just get rid of this piece altogether, right? And just change one of these to or equal to. That would have been fine as well. Okay? Okay. What equation are we going to plug this into if we're approaching 4 from the left, Nathan Z? The top one. Now what's going to happen, what will happen if I plug in 4? Or 0 over 0, indeterminate, which I think I spelled wrong yesterday, by the way. I think it's indeterminate. I can't remember. I always get this confused. Or indeterminate. I'll let you know by the end of the period. I'll Google it. So we never leave it as 0 over 0 and undefined. Just because we get 0 over 0 in that indeterminate case, that does not mean the limit doesn't exist. We learned yesterday that what's your follow-up? If you get 0 over 0, what should you then do? Starts with an M, ends with manipulate. What'd you say? Good job, Taylor. So we're going to factor the numerator into x plus 4, x minus 4, and the denominator stays the same, but then cancels. So now I can evaluate in that piece a little bit better. When I plug in 4, what do I get? 8. So the limit as we approach 4 from the left is 8. If we're going to approach 4 from the right, Nathan McMillan, which equation am I going to plug 4 into for part B? Right, also the first piece, right? Which piece? The first piece. So I plug 4 in again to the manipulated version, and I also get 8. So the overall limit, Stephanie, is 8. The fact that f of 4 does not equal 8 and actually equals 7 is really just a discontinuity piece. Okie doke. Any questions? I don't know why I wrote the homework on the front. Just so you know, it was up there on try this next exercise on your own, and then we'll see what we get. For all of them, limit as you approach 2 from the left, you're plugging into the first equation, 2 squared plus 6 is 10, good. Limit as you approach 2 from the right, you're plugging into the second piece, so 2 cubed is 8 plus 2 is 10, correct? Okay. Easy? Okay, try the next one. If you haven't already, sure. Something you already have. What do you think? Raise your hand if you got something different. Good. So the only way I changed up this one is I didn't baby step you through it. I didn't ask you to evaluate from the left and from the right just to kind of work your way up to it. You just have to know to do that on your own. So when you did evaluate it from the left, you got 7. And when you evaluated it from the right, you got 10, right? Yes, yes? And because those don't agree, does not exist. And the last one, raise your hand if you've already done it. Oh, good. Liam, what'd you get? Did anyone get anything different? Okay, 1 from the left is -1. 1 from the right is 3. Good. Is this easy? Good. Okay. Let's go back. We have 15 minutes. Okay, no problem. And do these from yesterday. These will become more prominent as we move forward. But it is important to have experience working with symbols and to kind of make sense of it, because reading math is not something that is second nature. It takes some training, if you will. So, on the bottom here, this property where the limit as x approaches a is just some number. For the function c is just some constant number. So what do you know about a function that's just a constant number? Right, that's the limit. That's just a horizontal line at c. So no matter what a value you're approaching, your y value is always just going to be at c. How about if your limit is, or if your function is just x? If you're approaching an a value, what's the limit going to be here? A. Yes. This is just a diagonal line, y equals x. So direct evaluation really works in both of these. If you plug a in for x, because x is approaching a, you plug a in for x here, there is no x, so you're just always going to get c. This one, you plug in a for x, and you're going to get a. That was like the example 4, the fourth example on the top. You just plug in 4, you get 4. You plug in, if it was x is approaching 5, you'd plug in 5, you'd get 5. So we're plugging in a, we get a. And then we're going to see examples where you're asked for the limit of a larger function that is two mini functions added together. And it's not the distributive property, but it kind of looks like it, right? You're not really multiplying the limit through. But you can take the limit of each function in isolation, and then when you add together those two individual limits, it will give you the limit of this whole thing in its entirety. Same thing with subtraction. Number 5, same thing with multiplication. Number 6, same thing with division. Okay? As long as the limit here obviously is not 0. Okay? Same thing if you're raising a function to a power. So if you're raising a function to a power, you don't need to find the limit of this whole thing. You can just find the limit of f of x first, and then raise your answer to the power. That would be the same thing. And then same goes for a radical, because radicals and exponents are technically the same thing. You don't need to find the limit of this portion. You can find the limit of just your function, and then take the nth root of that. Okie doke. They exist. I'm showing them to you. They will be used sparingly. At moments, just to kind of explain things to you, I'll use them here and there. For the moment, I'm going to go to page 1028. Actually, on last night's homework, what number did we stop at? We did 1 through 41 odd. So, on tonight's homework, we are going to pick up on that page 1014. You left off at 41 last night, so we're going to pick up from 43. This is 1014 first. Okay, so you're going to pick up at 35, which you already did. Yeah, 35, you're going to do 5s and 9s, so 5 and 9. So you already did 39, right? So you're really starting at 45. I wonder why I didn't go 1 through 45 odd. Because these are all direct evaluation, so that's pretty straightforward. But then you're going to get into all this piecewise stuff. Okay, I don't want to talk about that. 35 to 49. What I want to talk about is this. So in exercises 55 to 56, use the equations for the functions of f and g to graph the function y equals f of g of x, then use the graph of f of g to find the indicated limit. So we need to first find f of g of x as an equation. So what do I do to get that? Plug g, right, working inside out, plug g into f of x. So when I plug that in, did we do this the other day? I know, I think I wanted to look more at it, though. Root x squared minus 5 is our function. And now they want the limit as x approaches 2 for that function. Can I just directly evaluate? Yeah, no problem with that. If I just plug in 2, root 2 squared is 2. No, root 2 when you square it is just 2. And 2 minus 5 is negative 3. Okay, for 56, same idea. G of x just gets plugged in. So it's going to be root x squared plus 3. And they want the limit as x approaches 1. So the square root of 1 is 1. 1 squared is 1. Plus 3 is 4. I know what I wanted to look at. What if they wanted the limit as x approaches a negative number? Right, we talked about that, right? So because you can't just cancel the square root with a square, we learned that very early on in the year, that wasn't allowed. It works with positive numbers, and we're finding the limit as we approach positive numbers. That's fine. But the square root of x being squared does not equal x all the time. If x is a negative number, that wouldn't be true. Got it? So if you look at this function, y equals, and I'll type it in exactly the way it is, the square root of x squared plus 3, and I do zoom 6, that graph doesn't exist at the negative numbers, right? Because that's not in the domain. You can't plug in a negative number. It's imaginary. So that part of the graph is quote unquote imaginary. You don't see it. So to talk about the limit existing where the function isn't even present is a weird thing to talk about. So we would just say it does not exist. Okay? How about this one? So we're given a picture of a function and then told to use the graph of g to find the indicated limit. So here's f of x. Let's look at 59. They're defining g of x as f of x plus 2. So what's your interpretation of that? Liam? So what's your answer going to be?
You find the value of x on the graph and then you plug it into the formula.
Okay, so what's the value of that on the graph?
Y.
Which is what? What number? 1. Okay, and then you're going to do?
1 plus 2.
And so the answer is 3. Good. So there's a couple ways to interpret this. First of all, you could re-envision g of x. Because think about transformations. What happened to f of x right here? Got moved up too. So you could just redraw the graph. 1, 2. You could just redraw the graph and call that g of x and go ahead. Find the limit of that new drawn graph as we approach 3. It's 3. Okay? Or this whole section is kind of getting at the properties that we just did. So if we're looking for the limit of g of x, we're essentially looking for the limit as x approaches 3 of g of x, which is instead f of x plus 2. Right? So you can use that property that says, okay, we can take the limit of each one of these separately. So the limit as x approaches 3 of f of x plus the limit as x approaches 3 of 2. And for this one, this is what Liam did, right? He looked at his f of x graph and found that the limit as you approach 3 is 1. Plus, and we should all know, that the limit as you approach any number, who cares what it is, of a constant is the constant, 2. Right? So it's a combination, just going back to these, it's a combination of using this property to split it up, and then within the second one we had to use that property, and then we also get 3. Make sense? So those properties, yes, you can use them, but you almost have to force it to use them because there's other ways of thinking about it that can get you that answer faster. Let me jump down to 65. It wants the limit of g of x as we approach 1. So that's the limit as x approaches 1 of technically f of 2 of x, or f of 2x. Now, which property would we be using here? I didn't give it to you. Oh, yes, I did. This one, right? So, looking at it separately, the limit as x approaches 1 of... No, I didn't give it to you. It's not the same thing. It's not two separate functions being multiplied. It's the f of 2x. So, it really doesn't use our properties here. We almost have to use... Well, how would you guys do this then? Who thinks they know the answer? I'm going to give everybody else a moment to think. Liam, I want to pick on somebody else. What's Megan been teaching you on the side? What? Oh, good. Well, I'm glad it clicks for you. Anybody else think they know the answer? Connor, what do you think it is?
0.
Jalen, what do you think it is? Negative 1/2. Liam, what do you think it is? I don't think it's any of those. Just kidding. What'd you say it was? Okay, so what's going to happen here is, did you do transformations? Yeah. Okay, so I'm going to just redraw this graph. Everything gets compressed by a factor of 1/2 horizontally. So this point is now here. This point is now here. This point, which is at 3, is now at 1.5, right? These are all, this point is just now here, so it just got pushed in. The 4 is now at 2, and there's our new graph. What is the limit of that newly drawn graph as we approach 1? 0. You see? I think to have it concretely, visually in front of you is definitely more helpful. You were trying to do it algebraically, but if you draw it and compress it, it becomes much clearer. All right, so you have your homework on the bottom of your notes. It's been a pleasure doing business with you.